Vanakkam. Welcome to this course on biomedical instrumentation. We have been looking at pressure measurement. In the previous video, we looked at intravascular or catheter tip based pressure measurement systems. In this video, we go a little deeper and we look at one specific type of catheter tip pressure measurement system, which is a piezoresistive strain gauge measurement system. Fundamentally, this video represents a sudden detour or a detail when compared with the previous set of videos. In the previous set of videos, we were looking at the types of sensors, we were looking at the classification, we were looking at principles of this. Here, we give a very specific example of a catheter tip pressure measurement system and describe the principle of operation and describe the Wheatstone bridge and its characteristics, which we have discussed previously, and we discussed the dynamic and the thermal performance of the piezoresistive strain gauge sensors. First of all, what is piezoresistivity? We have heard of piezoelectricity. Piezoelectricity essentially refers to this phenomenon wherein when a force is applied onto some specific material, it generates a charge or an electric field, a change in the charge or an electric field, thus reflected as a voltage. So, these are called as piezoelectric materials, these materials. Piezoresistive materials are those whose resistivity changes as a function of applied load or applied force or applied pressure. What is the difference between resistance and resistivity? High school physics. Do check this. For example, let us say you have a strip of copper. Can its resistance change? Yes. Depending on the geometry of that strip of copper, its resistance can change. Can its resistivity change? No, the answer is no. Why is that? Because it turns out that resistivity, also called as specific resistance, is a property of the material and it does not change for a metal. However, in this case we are looking at semiconductors which have specialized doping characteristics that have been doped with in a special manner such that its resistivity changes. That is, if you recall, the resistance R is rho times L by A. This rho is resistivity. This is for a metal. Geometry is reflected in L and A, whereas rho essentially captures a material property, which is resistivity. But for semiconductors, rho is also something that can change, and we exploit this characteristic of semiconductors to measure forces or pressure. So, it essentially converts the pressure changes, local pressure changes that happen in a small zone, into electrical signal by exploiting this piezoresistive property of the semiconductors. So, these are essentially silicon strain gauges that are only a few microns thick. That means this is high technology, not a few microns thick. This is placed at the fag end of the catheter, at the tip of the catheter. When the blood pressure causes a change in the property, change in the diameter, change in the geometry of this diaphragm, then this piezoresistive material essentially change its geometry such that its resistance changes. Now, we know from our previous discussion of Wheatstone bridge and strain gauges that these strained piezoresistors essentially act as two arms of a Wheatstone bridge. The other two arms are used as precision fixed resistors that are located in the catheter's electronics that are there, that are previously fixed values. And when this bridge is excited by some known voltage, the output voltage is essentially a function of the change in this resistance times the input voltage, the excitation voltage. Now, this imbalance caused by the change in the resistance essentially causes a change in the output voltage, or if the nominal resistance of the 4 arms are each of the 4 gauge arms, sometimes the number of gauge arms is increased to 8. This bridge arrangement maximizes the sensitivity, improves sensitivity in a very big way, even to really small teeny tiny changes in resistance. When will the resistance change by a teeny tiny bit? When the pressure or force changes by a teeny tiny bit. That there is very minimal common mode noise. So, it is a highly accurate and high fidelity pressure sensing system, because it turns out that the very minimal changes in resistance are very quickly and accurately captured with very high fidelity. If you recall from our previous discussion, gauge factor is what defines the performance, a critical performance factor or critical performance criteria for a strain gauge. How much the resistance changes in response to a strain is what defines the gauge factor. So, generally silicon piezoresistors, let us start with metals. We looked at metals. Metal foils have gauge factor of around 2. Some metals, constant tan we looked at, for example, has a gauge factor of around 20. But silicon strain gauges, silicon piezoresistors typically have gauge factors approximately 120, which is very high. So, they are extraordinarily sensitive, that can detect minute diaphragm deflections. Also, what is required is to ensure accuracy, one side of the diaphragm is exposed to air, essentially making sure that the gauge measures relative pressure rather than absolute pressure. Also, it makes sure that each sensor's zero offset, or the voltage that is measured at 0 millimeter mercury, and the scale factors are determined at the time of manufacturing, and it is given into the catheter's onboard memory or as a separate calibration file to the users. So, when you power, automatically this these factors, zero offset factors and scale factors, are loaded in the system without having the requirement for external zeroing or frequent recalibration, which is a common problem with these kind of sensors. With catheter tip sensors, frequent recalibration is a problem. With fluid filled systems, what is the problem? The problem is requiring constant frequent flushing. Saline flushing is required very often, and also they are very relatively slow. So, frequent recalibration is also something that is overcome, because we automatically load the offset voltage, zero offset voltage, and the scale factor automatically. So, these things are avoided. The design is so good, so highly specific, that it provides frequency response of well above 1 kilohertz, which means that any pressure change that happens at a time resolution of 1 millisecond, I can capture. Can I do that? Well, I mean, it's 1 millisecond I can capture, also account for Nyquist criterion and other such things, please do check those things. But the point is that 1 kilohertz faithfully capturing relatively fast changes, extremely fast changes in pressure, arterial pressure waveform, thus providing a relatively accurate and high fidelity measure of the waveform without having distortion. So, these are high SNR, not high SRN, high SNR and high fidelity measurements. Also silicon's piezoresistive properties and the temperature compensation resistor. So, you expect the temperatures in which this system is going to work. So, you design for that, you design such that this works between 35 degrees Celsius and 40 degrees Celsius, 36 degrees Celsius and 39 degrees Celsius. In that range you are going to have maximum thermal stability. Why is that? Because this is the expected range of temperatures of human bodies. So, the temperature compensation resistors are pre-designed with this temperature range in mind, so that you are going to have excellent thermal stability. So, we can have maximum or reliable long term monitoring. But what are some of the constraints that you are working with? Essentially, your design must find a trade-off between durability and sensitivity. Why is that? If the material is too flexible, then too many repetitions, too many cycles of measurements is likely to wear off the material. But if the material is too stiff, then what could happen is that a small change in the pressure is unlikely to cause a deflection in the diaphragm. So, you are essentially fighting a trade-off between durability and flexibility, durability and sensitivity. You are either going to have high sensitivity but less durable system, or you are going to have more durable but slightly less sensitive system. You will have to find that sweet spot that helps you achieve both. So, that is a critical constraint, because one more thing is that silicon strain gauges, because they are made of silicon is a adds more constraints, because this material property adds more constraints to design for you. So, you cannot have everything, you cannot have durability and sensitivity and high SNR and high fidelity and low cost, all of these are not possible. So, with this we come to the end of this video. In this video we looked at one specific type of pressure sensor at the catheter tip, which is the piezoresistive strain gauge sensors. We looked at the design of Wheatstone bridge. Sometimes we use 4-arm design, sometimes we use 8-arm design, and we looked at dynamic and thermal performance, that it has very high bandwidth, very high frequency response. 1 kilohertz, up to 1 kilohertz you are having a flat response, and thermal stability is ensured by designing appropriate compensating resistors, for example. We also looked at what may be one of the only disadvantages of the system, that you are essentially fighting a trade-off between the sensitivity of the system and the durability of the system between this. With this we come to the end of this video. Thank you for your attention.